Hello everyone, welcome back to my YouTube channel. It is your host, Dean Proctor, speaking in Dean's Dynamics course. We're going to be looking at an example today from Chapter 4 from the section Power and Efficiency, and we're actually going to be looking at how a car performs if it's always putting out maximum horsepower. So I have a few assumptions listed here that we can assume before we go ahead with the problem. We're going to be looking at the time needed to increase speed, generally. We're going to assume that the maximum power available is 10,000 watts. We're going to assume the mass of the car and the driver is 1,500 kilograms. And we're going to find the time it takes to accelerate from 10 meters per second to 20 meters per second, and then from 20 meters per second to 30 meters per second. We're also going to assume that there's no tire slippage. So the equation we are going to be using is equation 4.25 from the textbook, and that is T2 minus T1 is equal to m over p v2 squared over 2 minus v1 squared over 2. So we actually have everything we need to solve this equation, so we can actually just plug values in. So first we're going to be looking at 10 to 20 meters per second. So we have delta t equal to 1,500 kilograms over 2 times 100,000 Newton meters per second. We're going to have inside the parentheses 20 meters per second squared minus 10 meters per second squared. And then we can solve for this. Next, we're going to do 20 to 30 meters per second. Same thought process. We have 1,500 kilograms divided by 2 times 100,000 Newton meters per second. 30 meters per second squared minus 20 meters per second squared. Now we can solve this out. Let me grab my calculator real quick. Okay, now that I did this calculation, we found that from 10 to 20 meters per second, it takes 2.25 seconds, and from 20 to 30 meters per second, it takes 3.75 seconds. So we can see that there is, quite the discrepancy here. It takes much longer time to go from 20 to 30 meters per second than it does from 10 to 20. So why does this make sense? Well, it makes sense because it's not a linear curve when we talk about speed over time. If we wanted to look at it, the curve would look something like this, where it's going to flatten out over time. If we had speed right here and time right here, and it makes sense obviously, because just because you're accelerating, just because you have your foot on the gas, doesn't mean you're going to increase your speed over a certain amount of time. Eventually it's going to kind of bottom out at top speed. So I hope this helps. We just went over a quick example of power and efficiency in energetics of translating bodies.